Now that we've talked about our integration, we want to switch our attention to differentiation. So in order to do any type of differentiation with our vectors, we're going to need something called the del operator. You'll also sometimes hear this called the gradient operator, and this is our vector differential operator. It's important to note that this is not a vector by itself. And so in future videos, what we're going to look at is sort of our four basic definitions or uses for this. We're going to look at our gradient, our divergence, curl, and Laplacian. But for now, in this video, what we're going to do is we're just going to define our operator. And so we're going to define it in each of our three coordinate systems because it's going to be different in each of them. So what we're going to use for our del operator is this inverted Greek delta, which we call nabla. So let's start by writing our del operator for our Cartesian coordinates. So for our Cartesian coordinates, we have that our del operator is equal to the partial derivative with respect to x in our x direction, plus the partial derivative with respect to y in our y direction, plus the partial derivative with respect to z in our z direction. So what we can note is we have partial derivatives, but we don't have anything that we're taking the partial derivative of, and that's again because this is an operator. So what we're going to see is we're going to do dot products, cross products, multiplication of vectors with this del, and that's where we're going to have some function coming in here, for instance maybe a del A. But again, this del is just the operator. Okay, so that's our Cartesian coordinates. Now let's look at our cylindrical. So in cylindrical coordinates, we have that our del operator is equal to, in our row direction. So for our cylindrical and spherical, I'm going to write our unit vectors before sort of our other parts, and that's just because these unit vectors are going to depend on the angle, unlike in our Cartesian coordinates where of course our x, y, and z are our axes as well. So we have our row direction times our partial derivative with respect to rho, plus our phi direction times 1 over rho times the partial derivative with respect to phi, plus our z direction times the partial derivative with respect to z. So we have one sort of difference here with this 1 over rho term, but otherwise pretty straightforward, the same way as our Cartesian. So then finally, let's look at our del operator in our spherical coordinate system. So for spherical coordinates, we have that our del operator is equal to, and again, I'm writing my unit vector on the left because it's going to depend on the angle. So we have u of r times the partial derivative with respect to r, plus our theta direction times 1 over r, partial derivative with respect to theta, plus our phi direction times 1 over r sine of theta, times the partial with respect to phi. And so if you want to see a little bit more about how these equations are derived, you can look at pages 69 to 70 in the textbook. But ultimately, we're not going to be too concerned about how we derive these equations, but rather we're just going to be focused on how we can use them. And as we're going to see in the following videos, we have four basic uses that we have for these equations, or this operator, I should say.